If you could please type your name in chat so that I can take attendance later, I would really appreciate that. So before we finish up chapter 3, I have gotten several questions regarding contingency tables. So I thought it might not be a bad idea to look at a couple of examples of contingency tables. So we're going to look at a couple of problems in my open math. This first one is problem I think this is problem 10. I probably could look at it and see if it's problem 10, but I didn't take that screenshot. No, that's not problem 10. We're going to look at problem 10. Problem 9. So a couple of problems on contingency tables in section 3.3, 3.4 homework. All right, so the first one we're going to look at is problem 9. And this is a pretty simple contingency table problem. That doesn't mean that it's not giving you difficulty, but it is fairly straightforward. Now, what they didn't do in this example was they didn't give you the totals, and that's probably what's confusing the issue. So let me get PowerPoint up here where I can see. Okay, and thank you. It's been crazy with the COVID and now with the roads. My husband yesterday morning, as he was driving, he goes to Midwest City, works at Tinker Air Force Base, and he starts texting me using Siri, by the way, and he's saying, "Can you work from home?" I guess, maybe. I don't have classes. And he starts frantically texting me, "Do not get out on the roads," because by the time he got from Yukon, it took him an hour and a half to get from Yukon to Midwest City, and it took him 45 minutes just to get to Morgan Road. So the roads were that bad. And as you know from the news, 30 car pileups and stuff like that. Anyway, so I'm glad that we're all safe and at home today. All right, here we go. So this first example is a contingency table where they just give you some information in a table. So what you have here is 980 pedestrians who were killed caused by automobile accidents. And so what you have here in the 2 rows is that the driver who was involved in this accident was intoxicated. So the first row there, we have 43 drivers were intoxicated and the pedestrian were intoxicated. And we have 70 where the driver was intoxicated, but the pedestrian was not. So the total number of these accidents where we had someone intoxicated is 113. Well, we had the driver intoxicated.
What do you make?
I'm gonna put you on mute. When I hear that someone talking, I usually put you back on mute. Okay. Then no, the second row is that the driver was not intoxicated. 252 of those, the pedestrian was, the driver was not, and 615, neither one of them were intoxicated. So if you add those 2 numbers together, I don't know what that is. And I seem to have misplaced my calculator. 252 252 and 615. So 867. And the sum should be 980, which is the number that we're looking at. And then you can do the rows too. So we have 43 plus 252. So the columns, excuse me. So pedestrians intoxicated was 295. And not intoxicated was what, 685? And again, the 295 and the 685 needs to add up to 980. So what are we looking for? If one of the pedestrian deaths is randomly selected, find the probability that the pedestrian was not intoxicated. Okay, so what do we have not intoxicated for pedestrians? We have 685. So 685 of the pedestrians were not intoxicated when they were involved in an accident and killed. So what's the probability that they were not intoxicated, but they were killed? Well, the total number of instances we looked at was 980, and 685 of those were not intoxicated. So the probability down here that they were not intoxicated would be 685. So the total number that were not intoxicated and divided by the total number. So if I take my handy dandy calculator, 685 divided by 980, I get 0.69899795. Right, and they tell me to write as a percent rounded to one decimal place. So we're going to make this a percent. So we're going to move the decimal 2 places to the right, and then we're going to round the 8 up. So 69.9% were not intoxicated when they were involved in a traffic accident and killed. Okay. The next problem we're going to look at, I believe, is number 10. That's listed as 4. But this is a way more complicated contingency table. But they do give you the totals here. The following contingency table represents motor vehicles used in North America by country and type in 2016. So then they're going to ask you a series of questions, and then they're going to make you find probabilities at the bottom here. So they're going to make you, which is a lot of work, I'm sorry, it's a lot of work, but they're going to make you create a probability contingency table from the information in the contingency table above. So the first question is, how many vehicles are in Canada? All right, so what column represents Canada? Well, it's the second column here. So how many vehicles are in Canada? Well, that would be the 24,270. Okay, and then they say, how many vehicles are motorcycles? Well, that is the third row down. So motorcycles total are what, 11,449? How many vehicles are Canadian and motorcycles? So if we look at Canada, that column, and we look at the row motorcycles, where motorcycles in Canada intersect is the number of Canadian motorcycles. So they're Canadian and it's a motorcycle. So it's a motorcycle in Canada, however you want to say it. So where they intersect is 716. Then it's asked you how many vehicles are either Canadian or motorcycles. So you have to use a formula for this. So the probability formula we got was that let's write it out here. The probability of A or B, which we can write as the probability of A union B, is equal to the probability of A plus the probability of B minus the probability of both A and B. Or in probability notation, the probability of A plus the probability of B minus the probability of the intersection, A intersect B. So to find how many vehicles are either Canadian or motorcycles, we would have to find the probability, how many vehicles, just the vehicles, So we would find the number that are Canadian plus the number of motorcycles, and we'd subtract off from that the number that are both. So what do we have here? We're going to add the 24,270 and the 11,449, and we subtract off the number that are both using the formula for probability, but it's not really probability. So you take the total number of motorcycles, you add the total number of vehicles in Canada, the Canadian vehicles, and then you subtract off from that the 716. So whatever that is. I mean, we could take our handy dandy calculator out and figure it out. I get 35,300. 35,003, excuse me. Okay, and then you can do the rest similarly. How many automobiles are Mexican? 19,796. How many vehicles are not automobiles? Well, you got buses, motorcycles, and trucks. So you could add buses, motorcycles, and trucks. You could add those up, or you could take the total and subtract off the automobiles, and you'd get the same value. So you could do it either way. Okay, so then to find the probabilities, which I didn't take a snip of the entire probability table below, but to find, for example, the first cell down here, which it's not going to let me highlight. So the first cell down in that snip is you're an automobile and you're in the United States. Well, what's the probability that you're an automobile in the United States? Well, you take the number 961, I can't read, and you divide that by the total. So the first probability in this first cell probability that you're a vehicle, you're an automobile, excuse me, and you're in the United States is 112,961 divided by the total, which there's a bunch. And you have to continue doing this for the entire table. And so, for example, in that first row, the total, well, the total number of automobiles is 146,610. The total number of vehicles we're looking at is 312,865. So the probability that you randomly pick an automobile out of all these vehicles is 146,610 divided by the total, which is 312,865. And to find, for example, the probability that you're in the United States, you pick a vehicle in the United States, well, the 268,799 vehicles in the United States divided by the total number of vehicles, 312,865, and that gives you the probability if you randomly selected one of these vehicles, it would be in the United States. So that's what all those probabilities are below. Let's see what problem this was. Boop-a-doop-a-doop-a-doo. Well, that didn't help. I closed the whole thing. This was problem, it says 4, but someone listed as problem 10. All right. Are there any questions on that? Left off a parenthesis here. Okay. All right, let's continue then our discussion on chapter 3. We're going to finish it up this morning by looking at tree and Venn diagrams. All right, a tree diagram is a special type of graph used to determine the outcomes of an experiment. So a tree diagram is a way of finding your entire sample space. So all the possible outcomes of an experiment. It consists of branches that are labeled with either frequencies, so the number of outcomes, or the probability of that outcome. Tree diagrams can make some probability problems easier to visualize and to solve. So let's look at a tree diagram. Okay, so you have an urn. Does anybody know what an urn is? An urn's a big jar thing. In an urn, there are two balls, a red ball and a blue ball. So draw two balls one at a time with replacement. So you take one ball out, note the color, and put it back in, and then draw a second ball. So with replacement means that you put the first ball back in the urn before you select the second ball. So what does the tree diagram look like? So in that first draw, you get either a red ball or a blue ball. You get one or the other. Then you put it back in the urn, mix it up, and draw a second ball. So the second one, if you drew a red ball, the second draw, you can still get a red or a blue if the first one was red. The same is true if it's blue. If the first ball you picked out of there was blue, the second ball could still be red or blue. So the tree diagram looks like this. So the first line here is your first draw. So in the first draw, you can get either a blue ball or you can get a red ball. Now you put the ball back in the urn. So you're doing this experiment with replacement. So if you drew a blue out the first time, the second time you could draw a blue one or you could draw a red one. So this is the second. If you drew a red one out the first time, put it back in the urn, mixed them up. The second time, second draw, you could get a blue or you could get a red. So the sample space, the four possible outcomes are, you could get both blue. So you could draw a blue one, then a blue one. Or you could draw a blue one and you could draw a red one. So you could get blue, blue, or blue, red. Two possible outcomes. The second set of possible outcomes is you could draw a red one out first, put the red one back in there, draw the second ball out, and it could be blue. So you could draw red, blue. And then the fourth possible outcome is that you could draw a red one, put it back in, and then draw a red one. So you could draw red, red. So the four possible outcomes of this little experiment is drawing two balls out of an urn with replacement. Both of them could be blue. Or the first one could be blue and the second one could be red. Or the first one could be red and the second one could be blue. Or they could both be red. So what a tree does for you is it illustrates all the possible outcomes. So the first branch in your tree is your first set of outcomes. And in our case, our first set of outcomes is I could get a blue ball or a red ball. The second set of outcomes is the second branch. And in the second set of outcomes, we could get blue or red. no matter what the first outcome is, we could still get blue or red. So the second branch, we get blue or we get red, we get blue or we get red. So this tree diagram illustrates all the possible outcomes. And these are frequencies because you get one blue, you get one blue, a red, you get a red, you get a blue, and you get two reds. So these are all frequencies. So the number that you could get, you get one blue, then one blue, then one red, then one blue, or one red, then one red. So that's the possible outcomes. Now you could label this with probabilities if that, which we're going to do here in a minute, if you know the probabilities, we could do that too. Okay. Now, if your experiment, each branch has a lot of possible outcomes, then your tree diagram can get huge. I mean, really huge diagram. So it would be too many branches to deal with if there were more balls in the urn. So we simplify the process by having a branch represent multiple branches. So one branch can represent multiple outcomes. So in our urn, now we have 11 balls. 3 are red and 8 are blue. Draw 2 balls out again, one at a time with replacement. With replacement means that you put the first ball back in the urn before you select the second ball. So now what does your tree diagram look like? Well, now if you were drawing this as a pure tree diagram, your first branch would be, well, you could get 8 blue. I mean, the first draw could be, you got 8 balls in there, so you have 8 possible outcomes that are blue out of 11. So you could have 8 blue, and you got 3 red. So you'd have blue, red. So that would be your first branch. Well, that's really unwieldy. So instead of writing that down, we're going to write the frequency instead of writing 8 blues. So what we do is we write the frequency, the number of blues that you can get. So the first branch, the first draw, there are 8 blue balls in this urn. So you could draw one of the 8 blue balls. So the first branch here represents that you could draw a blue, and there are 8 of them in there. And the second branch represents that there are 3 red ones in there. So you could draw blue, or red. So that's what that 8 in front of the blue represents. Okay, now you put whatever ball you draw back in the urn, and you draw a second ball out. Now, if you drew a blue one out the first time, you could draw a blue one out. There are still 8 different outcomes in there that are blue. So you could draw a blue, or you could draw a blue. And that's what that second branch represents. There are 8 different blue balls in the urn. So the first draw, 8 of them are blue. In the second draw, 8 are blue. Now, if you could also, if you drew a blue, you could draw a red one out. And there are 3 red ones in the urn. And that's what this branch represents. So you could draw a blue, draw a red. So my sample space consists of, in that first branch and the second branch, my sample space consists of, there are 64 outcomes that could be blue. And the way we get the 64 is we multiply the frequencies together. So the first branch, there were 8 possible outcomes that were blue. In the second branch, there are 8 possible outcomes that are blue. So in total, I would have 64 possible outcomes that were blue. So 64 out of the total, which we'll calculate here in a minute, the total number of outcomes we could have in the sample space. 64 of those could be blue. Now, if I drew a blue one the first time and a red one the second time, that branch is 3 reds. So there are 24, 8 times 3, different possible outcomes where the first ball was a blue and the second ball was a red. Now, if the first ball you drew was red, there are 3 outcomes that are red, 3 balls in the urn that are red. And in the second draw, there are 8 different blue balls in there. So I could, my sample space contains 24 outcomes that are red, blue. So you draw a red one out the first time, and a blue one out the second time. Now, it's red, red, there are 3 outcomes that are red. If I put the ball back in there at the second draw, there's still 3 outcomes that are red. So the last set of outcomes in my sample space is that I could have 9 outcomes that are red, red. I'll spit this out. So we have 64 outcomes that are blue, blue. We have 24 different outcomes that are blue, red. We have 24 different outcomes that would be red, blue. Red the first ball, blue the second. And we had 9 outcomes where you could draw a red one and then a red one. So all these different outcomes is our sample space. So in total, our sample space consists of this many outcomes, 64 plus 24 plus 24, so plus 9, the total possible outcomes. And did I actually add this together? Somewhere. 121. So there are 121 different possible outcomes for this little experiment. So you can see, if you were actually creating a true tree diagram, where the first draw you'd get 8 blues, blue, 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 blue. Did I get 8 of those? 1, 2, 3, 4, 5, 6, 8. And then each one of these is going to branch out to 8. That your tree diagram gets unwieldy really quick. So that's why we use the frequencies in front of it instead of listing out all the different blues. Okay, so now you can look at your tree diagram and you can see that in the first branch, there are 3 branches where you could get a red. So in the first draw, since there are 3 red balls in the urn, there are 3 different outcomes where the first ball could be red. And that's what R1, R2, and R3 represent. And there are 8 different outcomes where you could get a blue on the first ball. So B1, B2, B3, B4, B5, B6, B7, and B8. So there's actually 8 branches. So this actually represents 8 different branches. This represents actually 3 different branches. So the 9 down here at the bottom represents that you get a red on the first, a red on the second, a red on the first, a red on the third, a red on the first, a red on the fourth, etc., etc. Or that you get a red on the second, that both of them are red. I spit it out. Okay. All right, so let's do a little bit of, so list the 24 BR outcomes. So that's right here. So if we look at the BR outcomes, then we could get on the first draw a blue, and on the second draw a red. So we could get B1R1. That's the first ball is a red, and on the second draw we get a red. Or the first draw is a blue, and this then we draw again and we get a red, or we draw a blue the first time and then we draw a red. So in each of the possible 8 outcomes, we can get a red. So red, blue, and then red, blue, then red, then blue, then red. So each of the B's, we can get a different red. So B1, R1, B1, R2, B1, R3, B2, R3, B2, B2, R2, I can't spit it out. B2, R3, B3, R1, etc. So if I draw a blue one out, then I have three different, the first one's blue. Then the second draw, I could get one of three reds. On the second outcome, I could get a blue. On the second draw, or the second outcome, I could get a blue, and each one of those could be red. I'm not saying this very well. Okay, the first branch has 8 blues, and each one of those 8 blues, you could get 3 reds. So you could get the third outcome. There are 8 possible outcomes, could be blue, and each one of those, you could get a red for the second one. The fourth blue, you could get 3 possible reds. The fifth possible outcome in the first draw would be that you could get a blue, and each one of those could be red, or 6, or 7, or 8. So the B1 represents the possible outcome that you get a blue, then you could get a red. So the first outcome could be that you get a blue or red. The second outcome, you get a blue or a red. Third outcome, you get a blue or a red, etc., etc. Okay, what's the probability that both of your draws are red? So the probability that you draw a red one out, you put the ball back in there, you mix it up, and what's the probability the second one is red? Well, there are 9 different outcomes where you get red, red from our tree diagram. Out of the total number of outcomes we have in our sample space, which we said was 121, so the probability that we get red, red would be 9 out of 21. 9 outcomes that are both red out of the total number of outcomes, which is 121. What's the probability of getting red, blue, or blue, red? Well, there are 24 outcomes that are red, blue. There are 24 outcomes that are blue, red. So since these are mutually exclusive, we're just going to be able to add the probabilities together. There's no probability of getting blue, red, and red, blue. It's one or the other. So this is the probability of getting a red, blue, plus the probability of getting a blue, red. Okay, the probability of getting a red, blue, there are 24 different outcomes out of the 121 that are red, blue. There are 24 possible outcomes in your sample space that are blue, red out of the 121. So that's 48 over 121. Okay, what's the probability of getting a red on the first draw and blue on the second draw? So here are my reds on my first draw. What's the probability of me getting red on the first and blue on the second? That's right here. That's red on the first and blue on the second. There are 24 possible outcomes where I get red on the first and blue on the second out of the 121 possible outcomes total. So this will be 24 over 121. Using the tree diagram, calculate that you get red on the second draw given you got blue on the first draw. So what's the probability of getting a red on the second given that you got blue on the first? where here is blue on the first, red on the second's right here. So there are 24 possible outcomes where you get red given you've already drawn a blue one out. So the probability of red on the second draw given you got blue on the first is 24. But what's my sample space? Well, now what is the sample space that I get blue on the first one? Again, I'm going to completely ignore these branches over here because those branches over there, blue is not on the first draw. So getting red on the second, given blue is the first draw, is only this sample space right here. So remember, this type of probability, getting the red depends on getting the blue on the first draw. So the sample space is not 121, it's 88. And it's 88 because getting a red, given that you've already gotten a blue, the total number of outcomes where the first ball is a blue is 64 blue and 24 blue red. So the total number of outcomes where the first draw is a blue is 88. So 24 over 88. It's a conditional probability. The sample space has been reduced to those outcomes that already have a blue on the first draw. There are 24 plus 64, 88 possible outcomes. 24 of those 88 possible outcomes are blue-red, so red on the second draw. Calculate the probability of getting a blue-blue. So blue on the first and blue on the second. Well, there are 64 possible outcomes where they're both blue out of 121 total. Calculate blue on the second given that it's red on the first. Well, that's this branch over here where you're getting a red on the first draw. So what's the probability that you get a blue on the second given you get red on the first? Well, there are 24 possible outcomes where you get blue on the second given the first is red. Divided by, well, now what's my sample space? Well, now the number of possible outcomes from that branch where red was my first draw, there are only 33. So it's 24 over 33. So again, the sample space is reduced. This is a conditional probability. So the second ball draw is dependent on what the first draw was. So what's the probability of me getting a blue given I've already picked a red out? So that's that second branch. So there are 9 plus 24 outcomes that have red on the first draw, 9 red, red, and 24 red, blue. The sample space is then 9 plus 24 or 33. 24 of the 33 outcomes have blue on the second draw, given the first draw was a red. Okay, so tree diagrams. Venn diagrams. We draw a rectangle that represents our sample space, and each of our circles represents an event. So suppose an experiment has the outcomes 1, 2, 3 through 12, where each outcome has an equal chance of occurring. Let event A be 1, 2, 3, 4, and 5, and event B be 6, 7, 8, and 9. So if we draw a Venn diagram, This is my sample space S. Here's my event A and my event B, and they do overlap because event A and event B have an outcome in common, and that is 6. So A and B is the number 6. Again, the event A consists of the outcomes 1 through 6. Event B consists of the outcomes 6 through 9. So these two events do overlap because they have an outcome in common, and that outcome is 6. So we put the 6 where they overlap. Okay, so event A are the outcomes 1, 2, 3, 4, and 5, and 6. So we put the 1, 2, 3, 4, and 5 over here. So we can see event A consists of the outcomes 1, 2, 3, 4, 5, and 6. Event B consists of the outcomes 6, 7, 8, and 9. And so in B, we would have 7, 8, and 9. So you can see here that event B, if we look at the circle, the entirety of B, the outcomes are 6, 7, 8, and 9. But we do have outcomes that are not in event A or in event B, and that would be outcomes 10, 11, and 12. So that is in the sample space, but it's not in event A or B. So now the entire sample space, if we look at all the numbers, are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, the entire sample space. So that's a Venn diagram that just represents events and their outcomes. We could also do this with this type of an example. Suppose an experiment has outcomes black, white, and red, orange, yellow, green, and blue, and purple. So let me say it again. An experiment has outcomes black, white, red, orange, yellow, green, blue, and purple, where each outcome has an equal chance of occurring. Let event C be the outcomes green, blue, and purple, and event P be the outcomes red, yellow, and blue. And there is an overlap in these two events. They share the outcome blue in common. So C and P is the set blue. C or P, when we could draw that too, C or P is the union of these two. So you just join them together. So I didn't say that over here, but let's go back. So A or B. So everything in A or B would be the set 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that would be A or B. So in this case, slow coming up, a C or P would be green, blue, purple, red, or yellow. Okay, so let's draw this. So here's my sample space. Here is event C. And they do overlap because they share an outcome in common. If they didn't share an outcome in common, they'd be two separate circles called disjoint. They wouldn't have any overlap, or the overlap would be empty, one or the other. So C is green, blue, and purple. P is red, yellow, blue. So blue is in the middle where they overlap. It's the event they have in common. So C would be green and purple. So now we can see green, C is green, blue, and purple. And P would be red, yellow, blue. So we would have red here and yellow here. So P is red, yellow, and blue. And what's in the sample space that's not in green, C or P? What do we have? We have black is not in C or P. White is not in C or P. Red is. Orange is not in either one of those. So we need to list orange out here in the sample space. Yellow is in P. Green is in C. Blue is in both. And purple is in C. So outside the circles, we have 3 outcomes in our sample space that are not included in either event C or event P. So this Venn diagram, a way of representing a sample space and the outcomes of an experiment, the events. Okay, let's look at some probabilities. Now that we've finished chapter 3, let's see if we can't figure some stuff out. So these examples encompass the totality of chapter 3. So the first example is, what is the probability? Should be a "the" in there. We want to be grammatically correct. What is the probability of getting 5 different cards, no 2, 3, or 4 cards of the same value from a standard deck of cards? Okay, and we're going to do this without replacement. Okay, so in a deck of cards, there are 4 suits: clubs, spades, hearts, and diamonds. And each one of these suits has a card that matches the other suit. What I'm saying is there are 4 aces in a deck of cards. So there are 4 cards that have the same value, 4 aces. There are 4 cards that are 2s. So there are 4 different cards that could be a 2. There are 4 different cards that could be a 3. There are 4 different cards that could be a 4, etc. Okay. So if I draw 1 card out of my deck, well, first of all, without replacement, we're going to use the multiplication rule. Because we're looking for the probability of the first card and the second card and the third card and the fourth card and the fifth card all being different. So we're going to use multiplication because this is an and. So the probability that the first card and the second card and the third card and the fourth card and the fifth card are all different. Okay, so we're going to multiply 5 probabilities together. The first card we're going to draw out of the deck. It's the first card we draw out, very first card. What's the probability that it doesn't match any other card? Well, the fact of the matter is we haven't drawn any cards out yet. So the probability that it's not matched another card we've drawn, since we haven't drawn any cards out of the deck at all, this is the first card, the probability that's different is 1. $52 out of 52. I guarantee you it's not the same as any other card I've drawn because I haven't drawn any cards yet. So the first probability is 52 out of 52. All right. So now what's the probability in the second draw that we get different cards? All right. So now, how many cards do we have? Let's just say we take out all the aces. Okay. So how many cards now are different if they're not aces? Well, there are 48 of them that it could be different than the first one. So let's say I draw an ace out the first. So we draw an ace. So the first card's an ace. Well, how many cards in the deck aren't aces? Well, there are 48 of them that aren't aces. Is that correct? And how many cards do I still have in the deck? Well, I haven't replaced the first card that I drew. So how many cards are still in the deck? They're 51. Okay, so let's talk about this again. So the first probability is you draw your first card out. It's the first card. It's different. Kind of intuitively, well, it's the first card. But what if you drew an ace out the first time? So the aces are gone. How many cards do you have left in the deck that are different than an ace? Well, there are 48 of them. But I drew one card out. So there are 51 cards still in the deck. So there are 48 different ways I can get something other than an ace out of 51 cards. Okay. How about the third draw? Let's say I drew a 2. So now, how many different ways can I draw a card that's not a 2? Well, now the 2s are gone. There are 44 cards that aren't 2s. Out of how many cards are left in the deck? 50 cards in the deck. See where this is going? So how about the third card? How many different ways can you draw a different card? Well, now there are 40 different cards in the deck out of 49. 49 cards in the deck because we drew out, now we've drawn out 4 cards. And then what's last? 36 out of 48. So the probability of me drawing well shuffled deck of cards and me drawing 5 different cards out of that deck and none of them being the same kind of card. So no 2 aces or 2 2s or 2 3s or 2 4s. So no pairs, no 3 of a kind, no 4 of a kind. They're all different. Is the probability that the first card is different than any other card is 1. I mean, it's the first card you draw out of the deck. But the second card, what's the probability that's different than the first card? Well, there are now only 48 cards left in the deck that are different than the first one. Because 4 of them are the same. 3 of them left in the deck are the same. So there are 48 cards that are not the same out of 51 because you didn't replace the card in the deck. Now, how many different cards on the third draw are different than the first 2? Well, there are only 44 cards left in the deck that are different than the first 2 out of 50 cards because you didn't put the first 2 cards back in the deck. On the third draw, how many cards are different than the first 3? Well, there are only 40 cards left in the deck that are different from the first 3 out of 49 cards because you didn't replace the first 3 cards in the deck. And then how many cards are different on the fifth draw? Well, there are now only 36 cards left in the deck that are different than the first 4 out of 48 cards still left in the deck. So you take your calculator out and you do 52 times 48 times 44 times 40 times 36, divide that by 52 times 51 times 50 times 49 times 48. And my handy dandy calculator says that this is 2,102 over 4165, or approximately, that's the one, right? Calculator's going to do this again. 52 times 48 times 44 times 40 times 36. Oh, I must have reduced it. It's a really, really big number. And then we multiply 52 times 51 times 50 times 49 times 48. And divide that by our answer before. And we get 8. Well, it's like watching paint dry, watching me use my calculator. 6560 311 875200. 50%. I don't know where I'm getting. I got something wrong here, folks. 52, 51, 50, 49, 48, 52, 48. Something wrong in my calculations. I get about 50%. I got something wrong in my calculation. I hate it when I do it wrong. 52, 48, 44, 40, 36, 52, 51, 50, 49. I've done something wrong. Does anybody see what I've done wrong? I don't know what I did wrong. It's this number here. Right there. 5071, approximately. Okay. The reason I'm questioning myself, on my paper, I have 0.7053. Yeah, I don't think that's right. So somewhere in my calculation, when I calculated it on my paper, I got the wrong calculation. I'm glad I did it with my calculator. Okay. 5071. Okay. Okay, what's the probability of 10 people in a room, nobody shares a birthday? And this is actually a very similar problem to the first one we did, the one with the cards. It's very, very similar. So again, if you pick one person out of 10, what's the probability that the first person has a different birthday? Well, it's 1. It's not till you look at the second person that you get a different probability. So the second person, so how many days are left in the year? Well, there are 365 days in the year, but there are only 364 different than the first person's birthday. So the probability that the second person you choose has a different birthday than the first person you choose, well, there are 364 days that are different than the first person's out of the 365. So the third person would be, well, now there are 363 days out of 365 that are different. So there's the third person. And you keep doing this till you get to the 10th. So the 10th person would be 356 over 365. So you take 365 times 364 times 363 times 362 times 361 times 360, etc., over 365, but that's 365 times 365 times 365 10 times. So it's 365 to the 10th power. So you take 365 times 364 times 363 times 362 times 361 times 360 times 359 times 358 times 357 times 356, and then divide that by 365 to the 10th power, because you got 365 10 times. And when I did that, I got 0.883. Hopefully, if I did that right this time. All right. And why did I multiply? That's a good question. Because the probability that you're looking for is that the first person and the second person and the third person and the fourth person and the fifth person and the sixth person, etc., have different birthdays. So since it's an and, we're going to multiply. So if it's an and type probability, we multiply. If it's an or type probability, we add. So we use the multiplication rule if it's an and. We use the addition rule if it's an or. So the probability of A or B, we would add the probabilities together. And if they can't happen at the same time, then the probability of A and B is 0. So that goes away. So if they both A and B can occur at the same time, then the probability of A and B is 0, and you get the sum, probability of A plus probability of B. But we were doing an and. So an and type probability, we multiply them if they're independent events. And these are independent events because one person's birthday doesn't depend on what the other person's birthday is. Okay. All right. Let's do one last one on a conditional probability. So I repeated Bayes' theorem for you. Bayes' theorem says that the probability of A and B occurring is the probability of A times the probability that A occurs given B has already occurred. Or you could solve this for the probability of B given A given B, the probability that A occurs given B already occurred, by multiplying both sides or dividing both sides, excuse me, by the probability of A. So the conditional probability, the probability that A occurs given that B has already occurred, is the probability of B times the probability of A given B divided by the probability of A. So with Bayes' theorem in mind, let's see if we can't find the probabilities in this example. The probability to have a type of cancer in a population is 0.03. A test for the disease is accurate 99% of the time if the person has the disease. And it's 98% accurate if the person does not have the disease. What's the probability of a person having the disease if the test result is positive? Test result indicates that the person has the disease. All right, so let's write some things down. The probability to have a type of cancer in a population is 0.03. So the probability that I have this type of cancer is 0.03. The probability that I don't have this cancer would be 1 minus 0.03. So the probability that I don't have this type of cancer is 0.97. Okay. Now what they tell me is that a test for the disease is 99% accurate if the person has the disease. So the probability that I test that I have this cancer, given that I actually have the cancer, is 0.99. So the probability that I test positive, given I actually have the cancer, is 0.99. What else are we told? We're told that if I don't have cancer, then it's going to indicate that 98% of the time. So if I don't have cancer, I'm going to get a no 98% of the time, 0.98. So the probability, let's write that down here since I'm out of room, that I get a no and I don't have cancer, or excuse me, that it's no given I don't actually have cancer, is the 0.98. Okay, and is that all the information I'm given? All right, let's look at this up here at the top again. So the probability that I test negative and I actually have the cancer would be 0.01. So if the probability that I test positive and I do have the cancer is 0.99, the probability that I test negative and I actually have the cancer is 0.01. And the probability that I test, I guess that's all I want to write down. The probability that I test, let's just leave it at that. Okay, so let's write some Bayes' theorem. So what am I looking for? I'm looking for what's the probability of a person having the disease if the test result is positive. Test result indicates the person has cancer. So what's the probability that I have cancer given that I tested yes? Okay, so Bayes' theorem says this is the probability that I have cancer and it's a yes, divided by the probability of a yes. So that's from Bayes' theorem. But the probability that I have cancer and it's a yes, well, that's the probability that I get a yes, given that I have cancer, times the probability that I have cancer. So we were given these two information. So this is again Bayes' theorem. These are all Bayes' theorems. So the probability of C and yes is the probability of yes given I have cancer times the probability I have cancer. So those two were given to me. The probability of yes given cancer is 0.99. So the probability that I test positive and given that I have the cancer is 0.99. The probability of having this type of cancer was what, 0.03? Whoa, I'm doing something weird. Okay, whatever that is. Okay, now the probability that I test yes, because I'm looking for this right here. The probability of me getting a yes on my cancer test is the sum of the two probabilities. What am I got here? Okay, so the probability I don't have cancer is 0.97. The probability that I'm not doing very good here. Oh, I'm going to have to leave this example. I'm getting lost in my calculations. Let's go to the tree diagram because I'm getting lost in my calculations. The tree diagram is where this thing comes into, since I only have 5 minutes left. Okay, so if we look at the tree diagram for this, and instead of using frequencies, we use the probability, I think we'll be a lot better off. Okay, so the probability of this type of cancer is 0.03. So the probability that I have this type of cancer is 0.03. So there's a 3% chance I have cancer. There's a 7% chance that I don't. Okay, now given I have cancer, the probability that I'm going to test yes is 99%. So the test is very accurate, is what it's telling me. So the probability of me testing yes, given that I have the cancer, is 99%. So the probability of me testing no, given I have the cancer, is 0.01. Okay, so there are my branches. So the probability that I have cancer and I test yes, I can get from the first branch. The probability I have cancer and I test no is the second branch. The probability that I don't have the cancer and I test yes is this second branch here. So the probability that I don't have cancer but I test yes is that leg of the tree. The probability that I don't have cancer and I test no, the test is very accurate. 98% of the time, it indicates that I don't have cancer when I really don't. But 2% of the time, it indicates I have cancer when I actually don't have cancer. So this tree diagram is a much better way of looking at this than just listing the different probabilities. But then we can list them. So the probability of having cancer is 0.03. The probability of testing yes, given I have cancer, is 0.99. The probability of me testing no, given I have cancer, is 0.01. The probability of no cancer, that I don't actually have this kind of cancer, is 97%, 0.97. The probability of me testing yes, given that I have this kind of cancer, is 0.02. So it's a very remote possibility that I test positive when I actually don't have the cancer. But there's a pretty good probability that if I don't have the cancer, that it test indicates that I don't. So there's a 98% of the probability that the test indicates that I don't have cancer when I really don't. Okay? So to find the probability of B given A using Bayes' theorem is the probability of B times the probability of A given B divided by the probability of A. So the probability of me having cancer given that it's yes is the probability of me having cancer times the conditional probability of yes, C given, yes given C divided by the probability of yes. Okay, so what I don't know here is the probability of yes. This is what I don't know. Okay, but I can figure that out by using Bayes' theorem again. So the probability of yes would be the probability of yes given C times P of C plus the probability of, so it's going to be this one, this branch, plus this branch. So it's going to be the sum of those two branches. So that's going to be 0.99 times 0.03, which is that first branch, plus 0.97 times 0.02, which is that next branch. So the probability of me getting a yes are those two probabilities of me getting a yes on that first branch and a yes on that third branch. So it's 0.01 times 0.99 plus 0.97 times 0.02. So the probability of getting a yes is down here. So if I take the 0.03 times 0.99 and I divide that by 0.99 times 0.03 times 0.02 plus times 0.97, what I get is 60%. So the probability of me getting that I have cancer, given that the test was positive, is 0.6. And that is the end of that horrible example that I messed up. But again, as soon as I draw this, it becomes so much clearer because Bayes' theorem, I mean, you got all these letters, it gets so confusing. But as soon as I draw it out, use a tree diagram, and instead of putting frequencies, I put the actual probabilities. It makes it so much clearer because you can see when I was over here just writing stuff, I got myself all confused. But as soon as I drew a tree diagram, then it made life a lot clearer for me. All right, are there any questions?